and let's welcome Bobby Brar to deliver today's technical seminar. Thank you so much, Bobby, for being part of this seminar series. Bobby will walk us through the Teledyne Scientific Advanced Technology. And as you know, Teledyne Scientific Company is a central R&D lab for Teledyne technologies. And Teledyne is a technology leader in high performance compound semiconductor devices and integrated circuits and high performance imaging systems for military, space, astronomy, and various other commercial applications. And let me also say a few words about Bobby. So Bobby received his Ph.D. in electrical engineering from UCSB in 1995. He did research on indium arsenide, aluminum antimonide, gallium antimonide materials for high-speed electronic and optoelectronic applications. So soon after he graduated, he joined the Nanoelectronics research wing at the Central Research Lab at Texas Instruments. And he worked on indium phosphide and silicon-based resonant tunneling diodes and field effect transistors. And these were for high-speed mixed signal applications. And Bobby joined Teledyne Scientific in 1999. He joined Teledyne Scientific to manage the advanced 3.5 devices, and today he is the president of the Teledyne Scientific Company. Before Teledyne Scientific, he was also at Rockwell, as I mentioned, Texas Instruments, and also Raytheon, and he has over 100 publications and more than 35 patents. Welcome, Bobby. The show is yours. Yes.
Thank you, Ajay. I'll get started giving you the overview for Teledyne Scientific. Of course, the actual work is being done by the list of illustrious folks that I've got here, including the fab. Couldn't do anything without these individuals. I'm merely presenting a lot of the work that they have done. I might drag in one or two references to some works that I started on indium arsenide aluminum tonight, just for the fun of it. So I tried to give this presentation with two viewpoints. One is just as somebody who is providing a service to the California Dreams Hub. So put my sort of Teledyne hat on and say, what can we offer that can be used by members of the hub or others in the community? And the other hat I tried to put on is also a little bit of a student hat, and to show you some things that may be a little bit different than what we've already published. So you should see some new stuff in here. I wasn't able to completely do justice to my student side because I was working on some charts on leakage in gallium nitride devices, which unfortunately I will not be able to show, but I'd be happy to present those at some other time. So with that, I'm just going to start out with this outline. You won't see this outline again. The charts are a little bit, I think they're organized enough, so we should be able to get through them pretty quickly. And then I'll have time for questions. If you have questions, put them in the chat and we'll figure out whether to answer them at the end or answer them during. Chances are I'll get answered at the end. So I'll give you an introduction to Teledyne, very short. I'll give you an overview of our indium phosphide and gallium nitride technology. And really my goal is, why should you use Teledyne's technology? How does it differentiate it so that you're not doing the same thing with two different foundries? In some cases, we would have things that are a little bit different than what you might get from the other industrial partners. I'll have one slide on integration because packaging, I'm going to be talking a lot about high frequency electronics, and packaging is a real challenge in those areas. So I'll say just very little about that, but enough to say that that we have some technology that will lend itself to packaging as well. And really, we want to make this accessible. And I'll try to tell you what is accessible. I will show you what is accessible, like in a foundry offering, what is something that we're developing. And both those things fit into the hub, because not only are we offering services on mature technology, but we're also trying to develop new technology in this hub. So lots of good opportunities to interact in the future. We've been here for about 40 years. It's high mix, non-CMOS, mostly 3.5s and MEMS technology. That's Teledyne's sort of core. We've got a 4-inch fab. We can do 6-inch wafers. We've got very experienced engineering and operations staff. The model basically is, go and get the high-risk government-sponsored contract R&D and try to develop technology that we can mature and offer them as foundry processes and products. So in some cases, we take our own foundry technology and we develop products out of them. A lot of this stuff is niche. Compared to silicon, everything is niche anyway. And then so because we have this capability, this fab, this 4-inch fab, potentially 6-inch in some cases, we have the ability to offer fab services. So we can do little runs, we can take over new processes that you might have and run them for you in an industrial setting and do some prototyping for you. There will be a slide later on where I'll show Teledyne actually has fabs that run 6 and 8-inch wafers, mostly MEMS related, but also some compound semiconductor fabs as well that are doing production. So we'll be happy to tell you about that later on. But the bottom line is that we may be able to also assist not just in the prototyping, but also in the actual productization of the technology or your technology. So you might see a little bit of repetition here, but in the high performance 3.5, so I'm talking about indium phosphide and gallium nitride here. These are the two technologies we focus on at present. We do offer foundry services. So the 1/4 micron or 250 nanometer indium phosphide bipolar transistor process has been running. We've run something like 40 MPWs, maybe not quite as many as 40 over the last 10 years. That's a lot of MPW runs, and you can get on that by talking to Miguel Ortiaga, who runs our foundry services here. And that 1/4 micron technology has sort of a 370 FT, 650 F max, which now in silicon germanium, some technologies are available out there that can do that. But this comes with a 4-volt breakdown, which you won't get in an CD technology. And you'll see some examples of what we can do with that. And we have a 50 nanometer indium phosphide hemp technology that's good for low noise amplifiers and front end. Like I said, we do 3 to 4 MPWs. We have fairly well exercised PDKs, and then we're also offering engineering runs. The engineering runs in the 130 nanometer indium phosphide DHBTs, 500, 1 terahertz. I'll show you some data on that. With about 3.5 volts breakdown BVCU. And we also have a GaN process with 100 nanometer GaN process. This one was developed for more of an X-band application, 100, 200 gigahertz, but we have technology at the same 100 nanometer gallium nitride hemp, which is suitable for up to W-band operation. So I'll share that as well. And then this wafer scale 2.5D packaging. The indium phosphide technology comes in this wiring interconnect. It's 4 levels of metal and BCB, and I think I have a slide on that later as well. So another way to look at this is indium phosphide HBT, and I'll talk about these. 250, 130. There's 2 variants of the 130. One is being developed under the DARPA LGAR program. We'd love to get to a 64 nanometer technology. It's not funded yet, but maybe there's an opportunity to do some of the work under this California Dreams. We've got the indium phosphide hemp, like I said, two variants, 50 nanometers for low noise, 300 nanometers for an RF switch. And the CE-GaN 100 or roughly 90 nanometers RF process for KAV and W-band applications. And that's available as an engineering foundry. We've got a power process as well I'll talk to you about. We also have a Schottky process, which is a 1.2 terahertz Schottky and gallium nitride. That's cool. Gallium arsenide Schottkys go 1.2 terahertz as well, or roughly close to that. But the breakdown voltage on this could be 50 to 100 volts. So how does that change how you look at mixers and multipliers today? And then wafer scale integrations I mentioned here. So another view of what we're trying to do. This roadmap is notional. Roadmaps need money. So we always trying to figure out how we can make these roadmaps come to reality. And that's why we can work with you. And this is another view of the very same thing. Nothing major here, so I'll get back to it. You'll see some of this later on as well. Okay, so cartoon form. Here's the 1/4 micron, the 130 nanometer, and the 50 nanometer indium phosphide hemp. I'll talk about these three first, and then we'll go to this multi-channel HEMT. Here, what I've shown is a Schottky gate on the side of the fin, and then these are the various channels, and you basically gate them by squeezing laterally. That's a bridge HEMT or a buried gate HEMT. This technology is good for switches. We have now focused largely in the last few years on this charge enhancement, and I'll talk about that. This is a more conventional transistor. Under the DARPA space program, we're developing a couple of really cool gallium nitride devices that are going to be important for high efficiency power conversion. One of them is a 10-volt P-gate. Why is it P-gate? Because it has to be normally off. And then there's a P-gate, which is 100 volts, and this is operational voltages. So the actual breakdowns may be 40 to 200 volts in this case. And this super heterojunction HEMT is something we'll talk about just briefly. It's a cool name, but it's really something very simple. It's got a P-type layer between the gate and the drain. And then this Schottky diode is also available. So if you'll see, we'll get back to these technologies. So let's start with the indium phosphide. So I said two of them, which is the 50 nanometer HEMT and the quarter micron, are available for foundry, and they're in products today. And the 130 nanometer is really more of an engineering process that we are running, and we are hoping to mature and make available. The wiring, like I said, is 4-level wiring with 5 microns of BCB thickness. You can do inverted microstrip on this, all top side, without having to worry about the backside metallization. There's gold-based interconnect, and the dielectric constant is 2.7. This has been run up to hundreds of gigahertz in this technology, 670 gigahertz in the terahertz transistor technology. And we can, of course, do wafer thinning and backside metallization, usually used for parasitic mode suppression in the substrates. So, okay, I've already said enough about this. Let's get into the fun stuff. This is the quarter micron technology. These are DC and RF figures of merit. You can see the FT and F max here as a function of current density, 400 gigahertz, 700 gigahertz. What's interesting here is the breakdown voltage. Like I said, BVCEO is 4.5, BVCBO, which is a collector base with the voltage that it can handle in reverse bias, is 5 to 5.5 volts. You can run this up to 2.5 to 3 amps per millimeter current density. Now, it's not a typical way you think about indium phosphide transistors, but it's a good way to think about the power that you can get out of the small emitters. Usually these emitters are 10, 15 microns for power applications. The beta on this technology is not as good. We'll talk about that very briefly later on. It's adequate for the applications we have. We have a high beta technology as well that can give you about 40 to 50 beta, but the RF technology has a beta between 20 and 25. This is the quarter micron technology here. The 130 nanometer technology, you take a little bit of a hidden beta. In indium phosphide transistors, the problem is as you have to increase the base sheet resistance, decrease the base sheet resistance with doping, you get more Auger recombination, and your beta takes a hit. And we'll talk about that a little bit briefly later on. So this is 500 to about 1 terahertz FTF max technology. And you don't give up a lot in breakdown voltage, 3.5 to 4 volts. Of course, Miguel will tell you the thing that really limits you is the on-state breakdown, not so much as the off-state breakdown. So you've got to watch your swing here. And we've done a lot of work in this technology so we can help make sure that designs are done in such a way that they're going to be robust. And you'll see products in this technology. Now, this is the quarter micron technology. These are products that we sell. So the typical use of this quarter micron technology would be for power amplifiers. They're very broadband. So this is showing you the gain across one amplifier here from 50 to 140 gigahertz. That's the magenta line here. These are chips designed by Zach Griffith, and they're available in test and measurement equipment that you use if you operate in these frequency ranges right now, provided by VDR. So this is our own internal product that we develop here. And these are available in extenders for network analyzers through VDI. And they use them in their products. Here's a more recent picture. I think you've seen this picture before. Here's a recent data point that Zach was kind enough to share with me from Theodore Reck VDI. This is as early as earlier this year, taking one of Zach's chips. This is an 8-way combined chip compared to a 4-way combined chip. The orange is for the 4-way. It's roughly giving you something like a couple of hundred milliwatts from 90 gigahertz to 140 gigahertz, very broadband operation. You can double the size of the chip, basically mirror image that chip. You have an 8-way combined chip, and you don't lose a lot in terms of packaging this part. If you were to measure it on wafer, this would give you more than half a watt over this range. This is a packaged device, showing you something in the range of about 400 milliwatts. This 8-way chip, you may be used to seeing, if you're calibrated a gallium nitride, you might think this is a large chip. This is about 2 millimeters by 1.6 millimeters. It's got 256 fingers by 1,300 microns of gate periphery. So that's one level set is, most of the chips that we're talking about in indium phosphide are going to be in that range of a few millimeters. That's what we can yield comfortably in our technology. We're not going to be able to do 100,000 transistors. That's just not possible today with the indium phosphide right now. It takes too much current. That'll be too much heat anyway. And the yield in our processes in our fab right now is probably limited to 100 to 1,000 transistors. So this gate periphery, if you had a 1 micron emitter length, that'd be something in the range of 1,000 transistors. And I'll show you examples of chips that we developed here that are in that range, of a few hundred transistors. That's kind of the sweet spot. So if you're thinking silicon, if you're thinking silicon germanium even, you've got to sort of think differently. This is a technology that's got very impressive bandwidth, very high, relatively high voltage handling compared to silicon and CMOS, and even indium phosphide HEMTs for that matter. But you have to decide that you're going to work with sort of what you can fit into a few millimeters by a millimeter, and typically that is going to be transistor circuits or amplifier circuits with the millimeter of gate periphery, and maybe about something in the range of hundreds to 1,000 small emitter transistors. So we'll give you examples of that as well. That was all quarter micron. I've got one slide on the 130 nanometer. This was under the DARPA ELGAR program, a paper written by Zach Griffith that won the industry paper award at the IMS. This is a 2-stage power amplifier at 220 gigahertz, which is the goal of the ELGAR program. This almost meets the goal. This is about 58.9 milliwatts with 23.6% PAE. And you can see 2 stages gives you something in the range of 10 to 12 dB of gain. The efficiency is a record. When we started out this program, we were looking at efficiencies sort of 10, 12%. And through working the technology and the transistors and improving the designs, improving the interconnect, which you can hear more about at GOMAC. I don't want to steal anybody's thunder, but this was published at the IMS. I'm happy to say the goals were 60 milliwatts and more than 20% power added efficiency, and we met those, and we moved on to phase 2 in that technology. So here you can see sort of the power measurements and the PAE measurements across the band, and it looks pretty solid here. So this is a nice record result in the 130 nanometer technology. So the 130 nanometer technology is just something that we haven't run as much, but it's starting to get a little more traction, because there seems to be a demand for indium phosphide for certain applications. I'll show you maybe commercial applications, and I'll show you that on the next slide. This is from Mark Rodwell's roadmap, which was published probably about 20 years ago, showing what one needs to do if you want to take the emitter from quarter micron to 130 to 64 to 32. And there's lots of opportunity here to improve the technology to get from sort of the 700, 1200 or 700, 1400 numbers down to, FDs and Fmaxes of 1400 gigahertz, 1.4 terahertz and 2.8 terahertz. Now, this is not trivial. We haven't actually done this. This is a very hard thing to do, but there's an opportunity to take this technology even further. So, and there's a roadmap to do that. So one application, maybe for the quarter micron technology or the 130 nanometer technology, is in this 200 gigabaud, where they need high-speed indium phosphide modulators. This is a paper by NTT showing that they can get the bandwidths needed, about 110 to 120 gigahertz bandwidth for these 200 gigabaud PAM4 applications. These are driving modulators data centers are needing more and more bandwidth, more and more speed and interconnect, and indium phosphide could be a player here. And this is specifically for a driver, so you need the voltage of 1 or 2 volts to be able to drive these modulators. It's not something that's going to be done by silicon germanium. We've looked at the flip side, which is looking at receivers within Teledyne, and yeah, there are some other options that are available for receivers because you're talking about small signals and noise becomes an issue over there. So maybe there's a brief mention of that a little bit later today, so you can listen to that later. There's one more thing you can do with these indium phosphide transistors, other than make power amplifiers. You can make analog or mixed signal circuits. But this is a slightly busy slide of something that I would call a EW transceiver. Okay, so it can receive signals on the left. It can digitize the signals. It has signal processing capability, and then it can choose how to scramble those signals and transmit them, and they can be transmitted through a DAC and a power amplifier. This little purple thing is sort of notional, saying that these power amplifiers, Peter Asbeck will of course appreciate this because this is an area he's done a lot of work, that you can actually take a look at what's going on the output of these RF power amplifiers and modulate their power supplies in such a way that they run at very, very high efficiency. This could be done in a small card, and if it's compact, it will need to be efficient because you have problems getting heat out of these kinds of things. So these lnAs and VGAs can be made in indium phosphide hemp or indium phosphide bipolar. This little dashed line is a holy grail. It's sort of a tunable filter, not an easy thing to do. People are working on these. It's a very challenging problem. There's no known solution right now, but the technology we have could potentially lend itself to solving that sort of holy grail box over here. Sample and hold trees, basically freeze the fast data and then allow higher resolution but slower clock ADCs to digitize. If you want to get a quick look at a very low bit rate, you can have a fast channel here where you have a low res ADC. These greens are all in the indium phosphide technologies. You can quickly digitize, and then through some low latency signal processing, you can put it out to a fast DAC. So this transceiver can have 2 channels. This is a high latency channel, and this is a low latency channel. You need timing, you need clock generation. All that can be done in fast indium phosphide because the edges will be sharper and you'll have less jitter. The blue stuff here probably best done in silicon. The green stuff could be done in indium phosphide, and the red here, I'm assuming it would be something in the range of high power gallium nitride. So is this a dream? Is this something that's possible? We've had some work in this area in the past, and we have built some of these green blocks, and that's what I will show you on the next slide. This slide is sort of an intermediate slide. Let me skip this for time consideration, but this really just shows you all that I mentioned to you is what are the various components that are in this transceiver that need to be developed and are still things that are challenging. So here are the building block indium phosphide ICs. Some of them say preliminary across them. This is a little bit dated. All these parts, these are essentially our 50 gigahertz family of parts, are available for sale through our website. So these are active balance, so going single ended to differential, clock buffers. In this case, we had a need for 20 gigahertz. So we didn't push that to 50 gigahertz right now. There are flip-flops, clock prescalers, and clock drivers. We've got track and holds. There are 2 varieties of track and holds with a 50 gigahertz input bandwidth. One of them has a very high sampling rate for RF kind of applications where you want to direct convert RF to digital. The other application, these are sort of 100 megahertz sampling rates for more test and measurement applications. We do sell a lot of these. It takes your sampling scope, basically puts a front end in it, and you can go up to 50 gigahertz input on these. And then some pulsars that are used and drivers that are used for one of Teledyne deploys boxes that basically does time domain reflectometry. We have in development up above 70 gigahertz samplers. We haven't been able to test them above 70 gigahertz. They give you something in the range of about 30 dB of square free dynamic range. These are again made for test and measurement applications. all the 200G and the 100G gigabaud stuff is going to be tested. Hopefully, we'll use indium phosphide technology to test these in the front end, because you need some dynamic range to measure all these PAM4 signals. So these building blocks are available today. If somebody wants to design into indium phosphide and they're interested in the IP, maybe it's something we can figure out how to make available so that for the R&D applications, we can make progress faster. You can take advantage of the learning that we've had over the last decade in this. Okay, just a quick comment on modeling. Maybe a little bit of a segue, putting some of my less of a business hat on, just maybe more about what opportunities we have. It'd be great, and it doesn't happen today, is to be able to think of a device all the way from band structure and go to nonlinear large signal models. That doesn't happen today. Modeling is a very time-consuming and somewhat expensive process. There are more and more complicated models trying to explain all the details of how a device operates. This is an example of this ASM HEMT model for gallium nitride. It actually takes something like 3 or 4 transistors to explain one transistor. This is a physics-based model. And I'm not disparaging it. I think these are the kinds of things you have to do in order to be able to get good modeling for devices, especially for gallium nitride, where you might have a situation that you have dispersion in the device, so it operates differently at RF and DC. You got to be able to capture all those nuances, and the way to do that is to make more and more complicated models. What would be really nice to be able to do in the future, pitch this a few times to the sponsors, say, okay, I'm going to go directly from the band structure, lay out the device in TCAD, and then somehow or the other, I can continue to do, without making a single measurement, I can pop out a model, which I can then validate against measured data, and hopefully close that loop, right? So essentially like a digital twin, but generates an actual usable SPICE model or ADS model. And it's hard because you start with band structure. There's a picture of the indium phosphide double heterostructure bipolar transistor published by Mark Rodwell. It hasn't changed much in the last 10, 15 years. We've been working on it. Emitter, base, complicated, sort of collector to base grade. It looks complicated, actually. In practice, it's relatively simple to do. And then the indium phosphide technology, you can see you're talking about indium phosphide in gas, highly doped, then transport in indium phosphide. These are hard things to do, but it has been done. I think it was under, Miguel will correct me, I think maybe it was under the DREAMS program. We were doing work with Doug Yoder, and Doug had basically taken these kinds of band structures and put them into a modeling capability directly from band structure, and modeled the transport of electrons mostly in the collector, so that we can optimize the swing for the bipolar transistor. Remember, I told you you do have problems in this area where everything's on and the current's on, the voltage is high, not just heating but other issues as well. So this model was done. These are electrons, as some of you know well. When you get into the indium phosphide collector, you basically get from the gamma valley, collect energy. You can go into the L valley. You might have a scattering event and drop down the gamma valley. How can you do it in such a way that you stay in the gamma valley? That was a thought process back in the DREAMS program. So we wanted to model this, and a lot of good intellectual work was done between Mark, Miguel, and Doug Yoder. And here's the kind of crowning piece of what they did there. This is an actual collector of the indium phosphide bipolar transistor that was being looked at that time. Here's the base. And Doug was able to put all the band structure in and run a model and actually swing and get currents and voltages predicted from band structure. I thought this was amazingly cool. You can see the electrons that are blue, they're staying in the gamma valley. The electrons that are orange are getting into the X valley, the L valley. This work at Georgia Tech, I think, was pioneering, and it's the kind of work that I think would be very good to look at under the program that we have right now. And it could be applied to anything. It could be applied to indium phosphide HEMTs or gallium nitride transistors. but essentially looking at these first principle calculations of including band structure, time constants, getting current voltage, large signal swings, and then being able to generate models without having to do a measurement. And then, of course, close that loop for fidelity, right? You don't want a model that's inaccurate, but it's hard when you're developing a new technology to get it to a point where it's good enough that you want to spend the money to develop a good design kit. It takes a long time. And if we can do something along these lines, we might be able to shorten that, because we'll be able to get a model that can be used by early adopters to evaluate and give feedback on the technology while it's still being developed. Oh, so just one sentence on, we'll put time check here. One sentence on indium phosphide HEMTs. Indium phosphide HEMTs are fantastic. You got the world's best indium phosphide HEMTs at the California Dreams Hub. The work done by Northrop Grumman down to 20 nanometers gate length, terahertz transistors, probably the only terahertz circuit in the world operating at 1.05 terahertz. The work we've done here on the 50 nanometer HEMT is probably a generation behind in terms of ability, but it's a very important and useful device. It gives you a good high GM. It's got decent breakdown voltage, and it's got a noise figure, F-min at 50 gigahertz, that's a dB. And this has been demonstrated on the DARPA MIDAS program with circuits. We still offer this technology as an alternative to somebody who wants to come and use, needs a low noise front end and can operate in the frequency range that's covered by the 50 nanometer. So I just wanted to let you know these are foundry processes that you can run today with Teledyne. Okay, so much for indium phosphide. We'll go to gallium nitride. Now, this is work done here by the team led by GaSb, and you're probably familiar with this. It's been published a lot, so I'll try to hit the highlights here. And unfortunately, like I said, I didn't get to the fun part, which I was looking at very carefully, which is the gate leakage in these devices. At the end of the day, maybe sometime later we'll be able to get into that. So there's two kinds of devices. One is sort of a 0.1 micron or 90 nanometer device. Like I said, this one was built for high breakdown voltage, 80 volts, so that FT and Fmax are 200 gigahertz. That technology is scalable on that same charge enhanced HEMT platform. You can learn more about it. Lots of publications are written. This is the CE HEMT technology. You can see you can get high transconductance over a broad current operating region. Transconductance is approaching 1 Siemens per millimeter compared to other technologies within the DIV, including HRL as well as Northrop Grumman. We also have this multi-channel switch. The multi-channel switch, you can see here, the current drive in the switch is 4.4 amps per millimeter. It has a fairly broad GM, and I'll talk about that very briefly as well. So both these technologies are built inside a wiring environment that has full MMIC capability, and we've been able to deliver on programs transistors with something in the range of 10 millimeter gate periphery across the chip. What's interesting about this technology is these dispersion numbers, and that's really what we think sets it apart a little bit from what you might typically get. We are now getting in the 100 nanometer CE HEMT process dispersion, and you'll see it in a second, less than 10%. At quiescent getting biases up to 15 volts. And we'll talk about that in a second. So the multi-channel or buried gate HEMT is the bridge HEMT. It's a cool technology. We started working on it about 7, 8, 10 years ago. Like I said, it has 4 amps per millimeter high drive current. It's got ohmic contacts, regrown ohmic contacts, which I'll talk about a little bit more. The on resistance for those is 0.37 ohms per millimeter, which is impressive. We're contacting all those channels. There are some clever things that GaSb did with this technology that we have not been able to capitalize on yet. So this is a Schottky gate, and the reason I was going to talk about gate leakage is because the Schottky gate is different from the standard HEMT gate where you have the aluminum gallium nitride barrier. So the leakage current tends to be higher. but the leakage current is more of a tunneling current. And that's what I was looking at. Because at that time, we were trying to get the breakdown voltage even further up in these devices, and we were having some challenges. Having said that, if you want to operate at lower voltages, there's something very clever that GaSb did, as I mentioned this technology. You can see here that these channels are tapered. And that basically means that they all pinch off, assuming that they all have the same amount of charge. They will pinch off at different values of voltage. The same channel will pinch off faster at the bottom and slower at the top. And so if you then take all these pinch-off voltages in the channel and you superimpose the pinch-off voltage, what you basically get is a very soft, smooth pinch-off, and you also get a very broad GM in this technology. And that could be of significant importance for very linear receivers. So this is looking at the transconductance of the device and its first derivative and second derivative, which is an indication of linearity in these devices. And this red curve is the superimposed value for one of these channels. And this is measured data shown here. And you can see that you've got a very broad GM with this very smooth transition with low GM double prime. And the broad GM is operating over something like -1 volt to about 4 to 5 volts. And this is typical of what well, I wouldn't say it's typical. I would say that this is reminiscent of the times when people used to use gallium arsenide MESFETs for receivers, and they used to get much better linearity than the gallium arsenide has. So this technology is in waiting. We're not running it right now for either switch applications or receiver applications, but it is something that is we can run. We've run many wafers, many lots perfecting this technology. Now, one nice thing came out of this, as we were trying to increase the breakdown voltage, we understood how to etch this material beautifully. And we were able to develop this charge-enhanced HEM technology that I'm going to talk about next. I would add one thing that GaSb always reminds me. You can also get the same kind of tapering effect, or I should say varying threshold effect, by just changing the charge in the channel, which you can control. But what GaSb reminds me is that it's nice to have a certain amount of charge. If you have too much charge, you get scattering, you get reduction in mobility. But having the right amount of charge in the range, a few 10 to 12 per channel, actually gives you the highest electron mobility and the highest velocity, and truly operates like a HEMT, even though it looks like a bulk device. It still maintains the separation between the charge and the transport electrons as well as the donors. And so you get the high electron mobility in this device, and you don't have to compromise that. And you still get sort of MESFET-like characteristics. Okay, so the charge-enhanced HEMT, this is the one that's sort of our bread and butter these days. GaSb has published this. There's some really nice overview paper written by Farid in the IEEE Microwave magazine coming out in October 2024. It's called Emerging GaN Technologies. These figures are taken from that paper. I would recommend you read them. It's got the who's who of the gallium nitride world here, writing a very nice paper. So in that, GaSb shows our charge-enhanced HEMT technology. We call it charge-enhanced because we actually dope the algan. I'll talk about that a little bit more in a few minutes. By doping the algan, we get lower dispersion in these devices. We have a very high performance of LPCVD silicon nitride that passivates the surface, also contributes to lower dispersion. And then the process involves a gate which doesn't have a sharp corner on the edges here, which reduces the peak electric field and also enhances not only the scalability of the breakdown with gate to drain spacing, but also helps with the dispersion as well. So these devices with the silicon doping in the algan allow you to get to 2 amps per millimeter on the knee. And the R on these devices with these N+ gallium nitride, regrown contacts is down in the 0.43 1 millimeter. I might say a few things on R-on in a second, so I don't know when those slides are going to pop up because I put them in last minute. Hopefully it'll work. The peak GM on these for the 90 nanometer technology is 1.2 siemens per millimeter. And at 0.2 amps per millimeter, you can see that you can get 0.6 siemens per millimeter. Why is that important? Because you typically want to bias for low noise applications. You want to bias at low currents. That's a sort of a typical place that you want to buy 10% IDSS, and you still get lots of GM to work with. So I think this technology is a unique capability that's available in our hub. We have a few people already designing into it. It's going to be offered in one of the projects that is being run. But I would hope that more people would get access to this technology and use it. So what does the charge enhanced HEMT performance look like in terms of large signal measurements? This is where I mentioned to you our conventional gallium nitride HEMT is got a dispersion of 33%, which means the RF current drops by 33%. It's already starting out at 1.2 amps per millimeter and drops by 33%. We may not have the best GaN HEMT technology. Other folks on this call or in the Dreams Hub probably can get this number down. I don't know exactly what it might be, maybe 20% or below. I would say that the technology that we're talking about here, measured from a drive current or knee current of 1.6 amps per millimeter, only shows a reduction of about 10% at a quiescent drain voltage of 20 volts. So low dispersion. In fact, for a while there, I'm pretty sure that it was the lowest dispersion. I believe it still might be. This is low pull data at Ka band, 30 gigahertz. You'll see something here that I hadn't seen before in a gallium nitride HEMT. I'll point out in a second. Now I'm starting to see a little bit more of that. In fact, the paper that you have in the Microwave magazine will have this feature as well. Bottom line is, before I get to that, the efficiencies here are in the range of about 54%. You're running 4 watts per millimeter. This is quiescent bias at 10 volts. These numbers are sort of represented here in watts per millimeter. Here's the 4 watts per millimeter at a drain voltage of about 10 volts, these blue dots. What is important here is that it's as you increase the drain voltage, your power density increases at a rate which is completely commensurate with the RF drive current of roughly 1.9 or 2 amps. So that shows you a nice scalable technology. You're not seeing a lot of dispersion. You wouldn't see this kind of scaling if you had dispersion in the device, because as you drive it harder, your RF current drops, your Pout drops. And you see that in some of the other data that we published over here. And this data may be a little bit dated, maybe about 6 months to a year old, but it's something that we think is unique about this technology. You can get up to 5-6 watts per millimeter, 15 volts on the drain, and it's completely scalable with an RF drive current of about 1.9 or 2 amps. So what was the one thing I was mentioning to you earlier about what's unique about this plot? It's you got to have the right eyes. You got to really love this plot to be able to pick it out. This red line is the gain. You'll see that as the input drive increases, the gain actually goes up. This is not typically seen in gallium nitride devices. With gain expansion is what you expect. It's textbook. There's other people on this call that will explain that to you in much more accurate detail than I could. All I know is that if you do have dispersion, you start to see clipping early, you're not going to see this. And so that was something cool to see. And it's really the same story. It shows that the device that's operating at DC is the same device that you're getting in RF, and the performance is textbook. There's a lot of cool things that are about this gallium nitride technology, even though it's got 10 to 11 threading dislocations that are very textbook. And that was one of the things I wanted to actually point out with my leakage data, but that'll have to wait for another time. Now, this is a large signal step from off to on. Now, this will be the conventional HEMT here, and the blue is the low dispersion HEMT. It shows that you can hit a very low, basically all the current drive that you want in a very short period. So nothing new there. So this is what we think can be the future for gallium nitride. Just a couple of comments here on gallium nitride ohmic regrowth, right? And this is a little bit of a segue that you better allow me, gosh, I'm running out of time. Maybe I shouldn't spend too much time on this. The 0.1 ohm millimeter is a fantastic resistance. You can see here, this device I showed you before, 2 amps per millimeter, operates up to 20, 30 volts. Down here in the bottom, I'm superimposing something from it almost dates back to grad school, though actually this is done by Josh Bergman. It was much better than anything that was done in grad school. This is an indium arsenide aluminum tungite transistor. Back in the day, we used to think, oh man, we've got 30,000 mobility at room temperature. We've got an indium arsenide pins in the conduction band. It's narrow band gap. You'll be able to make perfect ohmic contacts. Okay. Guess what? The gallium nitride technology that I just showed you has the same ohmic contact resistance to these devices. I will say that a lot more money has been put into the gallium nitride than the indium arsenide. But at 0.1 ohm millimeter contact resistance, 0.4 ohm millimeter on resistance, you're seeing the gallium nitride technology operate at low voltages as good as any of these narrow bandgap materials, which I thought would be impossible back in the day. Why bother about indium phosphide then? Why bother about indium arsenide? Well, indium arsenide has probably been overtaken by indium phosphide channel devices. The reason is, you can see this paper by Keisuke at 20 nanometer gate lengths, low voltages. We're talking about 100 to 175 gigahertz FT at 0.2 amps per millimeter, at 0.2 amps per millimeter, 0.2 volts on the drain. You're getting roughly the same values from indium arsenide, aluminum, and timolite. Okay, so gallium nitride, of course, it's at 20 nanometer gate length. This is 100 nanometer gate length. This is work done by Josh Bergman. And of course, the indium phosphide is still the best, right? These are HEMTs, 0.2, we're talking about 350 gigahertz. And of course, the answer there is obvious. It's the velocity. The electron velocity is much higher, and so you've got higher RF figures of merit in indium phosphide than you have in gallium nitride. In some sense, this shows that indium phosphide is still the king at low voltages, but watch out. There's maybe more things you can do in gallium nitride than we thought possible. In terms of contacts, regrown contacts, the indium phosphide technology I showed you before, one of its limitations, of course, in scaling is going to be the base contact resistance. Not just scaling the FT and Fmax, but also improving its noise properties, which have become maybe more important, like I said, in those receiver applications for 100 gigabaud or 200 gigabaud applications. So there's some, I wouldn't call it low-hanging fruit, but like an obvious thing we need to do in indium phosphide HEMTs. And I think Mark and Miguel have been talking about this for a while. Get some money, develop some base regrowth. It's standard process now in gallium nitride to get the highest performance, especially for applications for the DoD. We need to get the same technology here to increase, to basically be able to dope the extrinsic base and not take a hit in the beta. Remember, the beta is 10, 20, 30. We don't want to take a hit in that beta. In fact, we want even higher beta, but we don't want to give up the base sheet resistance. And the only way to do that is to have the extrinsic base. Okay, so that's a plea. All right, so finishing out the gallium nitride, under the DARPA space program, Keisuke has been doing some really good work here with the team. This is a normally off device. You're not making this device for RF for a number of reasons, and I'll tell you in a few minutes, but you definitely need a normally off device. Again, with the N+ GaN regrowth, you're managing very low on resistance, less than 0.5 ohm millimeter. The threshold voltage is positive 0.7 volts. The breakdown voltage is 43 volts on this. Very low gate charge and record values for R on QG. You can look at these at your leisure later on. This is a low side switch or a 10 volt operation device. Maybe if you want to do a 50 to 1 volt power converter. This is bigger brother wants to operate at 200 volts. And it's very critical now as you extend the drain out that you can increase the breakdown voltage. And that's why just watching this portion of the device, not just the curvature of the gate foot, for example, but also really how you passivate this and how you build these transistors in such a way that you can actually increase the gate to drain resistance and get the breakdown voltage for a lateral device. It's not that easy. So one of the things that people have talked about in these devices is putting field plates, of course, and that's done in the RF world, okay? The other thing you can do is put something known as a super heterojunction. And both these field plates or super heterojunction, hold off on the super heterojunction for a few minutes. All they basically do is take the peak, this is the band bending, this is the energy band. So the electric field is high here. It's the slope of this band diagram. And essentially the field plate of the superheterojunction basically gives you a flatter electric field. And by having a lower peak electric field, you should be able to increase the breakdown, or at least scale the breakdown due to plane bias. So we'd like to do that. In the RF world, that's done by field plates. In the RF world, you can't really do that when you want high gain because the field plate has capacity. So enter the superheterojunction. Okay, the superheterojunction, the way I understand it in my simplified way is, look, you've got a layer that's not metal. It's P-type gallium nitride that's between the gate and the drain. When that P-type gallium nitride is operating at low voltages on everything, it's got P-type carriers on it. But the minute you apply a large drain voltage, you put a reverse bias, let's say it's gate connected between the gate and the drain, and you deplete your carriers in the channel, but you also deplete, very important, you also deplete the P-type layer. And so the P-type layer changes from a bad metal to a pretty good insulator. And so you can take that device and get what you want in terms of the breakdown voltage at low currents, but at low voltages, and you can have the charge here, so you can have good low R on. But as you apply the voltage and you reverse bias this device, you don't take the hit in the capacitance associated with that superheterojunction. Now, this unfortunately will only operate at relatively, the RC time constant associated with this P-type layer is not going to allow you to operate this at gigahertz switching speeds, but it will certainly operate at megahertz switching speeds. This is what we're trying to develop under the DARPA space program. And if everything lines up, we'll be able to offer this technology in a few years. And what it will do is allow you to have low R on and low C off, both important applications, both very important for high efficiency power conversion. And you'll still manage to have like 200 to 300 volt breakdown. Okay, so that was a lot about gallium nitride transistors. I'm running out of time here. Only a few more slides left, I think. This is the gallium nitride terahertz Schottky, like I told you. This has got a cutoff frequency of greater than 1 terahertz and a breakdown voltage of, you can read it, 70, 80 volts. I wish more people were using this. This is available. It's a product. You can buy it. You can put it in your lab. You can reverse bias it. You can hit it with something and see if you get, second, third, fourth, fifth harmonics out of it. But it's really something we'd like to be able to see used in the industry. I don't have a lot of time left here, but I do want to talk about this. Peter Asbeck put together or I should say, deconstructed the puzzle about where the electrons come from in the gallium nitride. Well, you have a basically undoped gallium nitride has charge in it, enough to make good transistor. And that is because you've got a barrier height at the surface, which is set. And then when you make algan on top of gallium nitride, the algan tends to have a polarization in it. It comes from piezoelectric effects as well as spontaneous polarization. The bottom line is there's a field here, whether you have charge in the well or not. At some point, that field and the delta EC connect up to drop below the Fermi level, and you get charge in it. So you also get the 2 DEG. But you would have this band bending even if you didn't have charge in it. That's what the polarization does for you. Okay, so can we do more with polarization? We've been playing around over the last few months, years, just looking at the kinds of polarization fields, and you probably know it, so I want to repeat it, right? I want to repeat it. Algan has a polarization field, putting it that way, as 0.3 electron volts per nanometer. That's X equals 0.3. If X was 0.1, it would be roughly 0.1 EV per nanometer. In other words, you'll drop 0.3 EV over 1 nanometer, just because of the polarization field. In aluminum nitride, it's 1 electron volt per nanometer. That's the entire band gap of silicon in 1 nanometer without doping. Okay? And that is used to enhance the charge in our HEMS. This would be a fairly typical band diagram for gallium nitride HEMS. Okay. We haven't really done, yes, people have been thinking about it. Umesh has published papers where you can get both P and N type, but really, this material and its polarization properties are so remarkable that sometimes we forget that there's more opportunity here. And this is just for illustrative purposes, for the fun of it, for the grad students out there. This would be just something you throw into BandEng, which is a beautiful program written by, available from UCSB, from Professor Mishra's group, one of the students. This just shows a gallium nitride surface, aluminum nitride running at this 1 eV per nanometer. You get a huge offset between aluminum nitride and indium nitride. I'm not even saying you can build something like this. I'm just pointing out what can be done in these kinds of materials. Who knows what the band gap of indium nitride is anymore? I think it's about 0.7 eV. I don't know if you can grow it, but maybe you can grow InGaN. Okay, maybe you are smarter than me and you can figure out other ways to do this. You could have electrons, 10 to the 14 of them. Again, like I said, I'm not making a device, I'm just having fun. You can have holes literally a few nanometers away, right? This is in angstroms, 20 to 50, right? So that's what, 30 angstroms, 3 nanometers, 10 to the 13 holes. That's not a useful device, okay? Well, maybe I was thinking, okay, you could put a forward bias on this thing, you can have the electrons and holes overlap, and you can make a laser out of it without injecting any current, or I'm sure you have to inject current because you have to resupply the electrons in the holes. But it'd be something cool to look at, right? Maybe you can make complementary devices this way. I know Umesh had been looking at that a long time ago. Anyway, I just want to tickle your thinking and ask you to think about what more we can do with these polarization devices, given that the massive polarization fields that are available just by virtue of the way the material is made. I'll finish with a few more slides and we'll take questions. I apologize, I did run a little bit over. This is the packaging technology. I'll leave it for you to look at. You can bury dye in silicon wafers, and we can do the same BCB dielectric and metal stack above. And now you can get 200 gigahertz die to die if you want it, or 500 gigahertz die to die. And you can place that contact anywhere you want it. You don't have to have it at the pad. You can have it in the middle of the die if you want. So there's lots of capability here. We've been working on this technology for a long time. I would say there's a version of it that is fairly mature and we can offer it as a process. And then the other versions that people want to tweak, and those ones always give us trouble because it's not an easy process to run, but it is something that might be the future of packaging in high frequencies. I showed you this already. Teledyne Scientific Company microfabrication capabilities. We offer foundry processes, and we also offer prototyping services. And I think I'm going to just end with that, so I have at least a few seconds for questions. Thank you for your attention.
Oh, that was a great talk, Bobby. It was a good overview. Let's see. People have questions, I guess. Any questions?
Andy Carter clarified it was DARPA Dream. Yeah.
Yeah.
I getting old. I'm starting to forget my DARPA programs. You're welcome, Dave. I was done a lot of work both at Teledyne as well as HRL and Northrop Grumman represented here. That summary paper that's in IEEE Microwave magazine is worth a good read. It came out in October 2024. It has a lot of different technologies. Oh, right. So sorry you missed it. What MEMS products or MPWs do you run? Most of the MEMS work that we're doing, where we haven't done MPWs on MEMS, but we've got the MEMS for the deep reactive ion etching for the packaging capability, where we etch into silicon wafers and drop dye into that. That can be run as a foundry process, but probably not as an MPW because there's just a lot of dye involved and it's not that easy to get people. But what we do in MEMS is we will interface directly with other outside MEMS users, and we can run either process steps here, mostly DRIE, but we can also do wafer bonding. We can do micro lensing, grayscale lithography, etc. And so we can do process steps. And in cases we work with small companies, prototype their technology here, which has allowed them to then get additional funding and move to a production facility elsewhere. I will say that there is a very strong MEMS capability in Teledyne, and so we have an 8-inch production line in Teledyne also that we can transfer technology from here to that production line, and we've done that for or gyros, MEMS gyros.
Thank you.
Yeah, the gallium nitride products to market. Yes, the answer is that anything that is not already offered as a foundry service, where we're also building products and doing MPWM, there is a lot of opportunity for maturation. And I'm sure there's a lot of people here that would like to sign up for that maturation money, because that's hard money to come by. And so maybe together as a hub, we can say, okay, that technology is actually worthwhile. And it would be worth taking the money, investing it to mature that process. Even the CE hemp technology, which is very, very promising, at this point, we're not offering MPWMs and standard foundry runs. It's more of an engineering foundry run, in which case we're saying, hey, we haven't run this a lot. We need to get more statistics. We need to be able to validate the models. And that would be a beautiful technology to take to TRL 6, 7, and MRL 6 and 7. And the Moses 2.0 and the hub, I mean, that's one of the reasons why I think I'm excited about this Dreams program, is because it can provide access and also maybe allow us to have the funds to mature technology. But it would be technology that would be useful already, because you have this user base.
Thank you, Bobby. Any more questions? Any other questions for Bobby? Okay, it seems there are no more questions. Thank you once again, Bobby. I just want to highlight that, if you go back to the previous slide, Amy, so those people who have not registered to the technical seminar, if you register, then you will not miss any emails. So that's probably very important, that if you have not registered, please register. Next slide, Amy. So our next technical seminar is on February 21st.
I don't know if we're sharing. I have to stop sharing. So you know,
I think Amy took control
Amy
over
did
it, I
it.
guess.
Yeah, okay.
Amy did it. Yeah. So the next seminar is from HRL, from Jameson Moon is going to give the talk. So that's going to be another exciting talk. Thank you so very much, John. And thank you everyone who participated today. And thank you, Bobby, once again.
If anybody has questions, they can email me, or anybody on that list and ask questions. We'll be happy to respond.
Thank you.